Assalamualaikum and a very good day to you guys. Okay, right? So this is your last lecture for thermodynamics 2. Okay, so this is lecture 7 on the introductions to molecular thermodynamics. Okay, right, the objectives of this lecture is to introduce you molecular theory of fluids and to instigate second-order coefficients from potential functions and to initiate understandings of microscopic views on internal energy of ideal gases and to establish understandings on thermodynamic properties and statistical mechanics and to instigate hydrogen bonding and charge transfer complexing and to comprehend behavior of excess properties and to study the molecular basis for mixture behavior and last to commence molecular simulations for vapor liquid equilibrium, okay, on VLE. Okay, so for the introductions, okay. So classical thermodynamics is a deductive science in which the general features of microscopic system behavior follows from a few laws and postulates, right? And then the properties of individual chemical species and their mixtures, and this may be presented either as a numerical data, there are estimate table, or as a correlated equation, a PVT equation of states. Right? We have done a lot on that. And the usual source of property value is experiment, but they do provide insight on into why substance exhibit their observed property value. So basically, where we use the PVT to find the data, right? And then we compare it to experimental values. Okay, so if the correlation is more than 75%, so we can believe that our equations are uh, reasonable, okay, right? So we can generate that. Okay, one of the reasons why we use equation rather than all experiments is that experiment is very expensive. So to reduce cost or to find or to study the ideas of the behavior of mixture, then we can use the equation first, okay, right? So we can model it, and then with that then we can manipulate it more, okay, right? So with this the experiment is just to check whether our model is acceptable or not. Then from there, then we can manipulate the equation, and then if we got the result, and then we might counter check it again with the experiments. So the more experiment you do will be more expensive and the longer time it will require. So this is the problem in thermodynamics and why thermodynamics are very important, because and then why we use a lot of the equations. Okay, molecular theory of fluid into molecular forces and pair potential functions. Okay, ideal gas is categorized by the absence of molecular interactions. So as I have explained to you before that in ideal gas, there's no intermolecular interaction between the molecules, right? So it's independently. So this energy is associated with the individual molecules and result from their motions. But somehow in real gas, this is not true because there are interaction between these molecules. So and also energy that is shared among them because of the intermolecular forces. So that's why in real gases and ideal gas are when you do the calculation is slightly different. Okay, right? But it's much easier to do the calculation in ideal gas condition, and then we compare it to or to relate it to the real gases. And then this intermolecular potential energy is associated with collections of molecules and in the form of energy that reflect the existence of such forces. Okay, well established is the fact that two molecules attract each other when they are far apart and repel one another when they are close together. Okay, electromagnetic and origin, the intermolecular forces represent interaction among the charge distributions of neighboring molecules. Okay, so this is the graph actually. Okay, so this is where the sigma here indicates that when the molecules when it too close to each other start to repel. Okay, so that is denoted by the repulsion here denoted by this mu here. Okay, right? So when it close to each other, but when you uh, further apart it a bit, and then they become neutral. Okay, right? So there's no repulsion or attraction. So that is symbolized by this sigma here. Right? But when it even further away, then we can feel the attraction is stronger. Okay, right? The further away, then will be the strongest attraction is when the distance is r not here. Okay, so this the highest attraction will be the epsilon here. But the further than that, then it lost the attraction, and toward the end, when it comes to infinity, there's no attraction at all. Correct? No attraction or no repulsions. Okay. Okay. So this is what we denote by the graph here. Okay, right? So these intermolecular forces can be written in terms of this Fr d mu r over dr. Okay, here. So the F represent intermolecular repulsion, and the negative F and intermolecular attractions. Okay, okay, right? Uh, okay, so that's it. Okay. So and this, okay, right, for the repulsion and attractions. Now we can calculate it using this unit here. This is called Lennard-Jones. I'm sorry, Lennard-Jones LJ, or 12 over 6 square potential function. Okay, right. So the 4 epsilon sigma here over r minus 12 and then 6 here. Okay, right. So this 12 is the term for repulsions. Okay, and then this is for the attractions here. Okay, okay. Okay, why this thing happen? Because of the, in the molecules, the inside are positive and the outside are negative, isn't it? The electrons here. So when it too close each other, then it repel. Okay, nah? The charges repel each other. When it move further, then start to be some attraction here. Okay, this is what we call as the electrostatic potential energy of interaction, or we call it mu L. Is we can denote with this equation here, where QR is the charge of distribution, QJ is the charge in distribution B, and RJ is the separation between QI and Q uh, J. Okay, right? So we have A and B. Okay, right? Okay, so and epsilon naught is the electric permeability of vacuum, a physical constant equal to these values, okay, right, in column volt. Okay, so all right, so for the Leonard Jones potential, okay, this is the ratio here, and this is okay, you can see that this is the repulsion and this is the attractions. Okay, right? So when it very close, it repel. When it very far, it attracts. Okay, right. So electrostatic also potential also can be calculated using this equation here, which is -2 with kt, right? It's a function of k is the Boltzmann constant equal to this value, and the temperature, inverse of the temperature. So what does it mean, right? As the temperature increase, what happened? This value will be decreased. Okay, right? So it produced several results. Right? Even though the distribution are electrically neutral, there is a net attraction between them. Okay, right? And the dependent of mu L on charge distribution orientation become an averaging and R minus 6 dependence. Okay, so as given by equation UL varies with T minus, hence the magnitude of permanent dipole attraction decreases with increasing temperature. Okay, this equation is the simplest example of direct electrostatic potential for two neutral molecules. So the dipole moment charges as important properties. Okay, 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 right. So for the dipole moments, okay, right, we can measure is, okay, right, for a molecule in charge with plus Q is separated from minus Q by distance L. The dipole moment mu equal to QL. Okay, mu has the dimension of charge time length. So the unit is coulomb meter. So however, is normally reported by device D of the 1D is equal to this value. Okay, right? 3.3357 10 power minus 30 coulometer. So a molecule with a non-zero dipole moment is called polar. Okay, the water, we know that water is very polar. Acetone and acetone, acetonitrile, okay, is very high, 1.9 D, 2.9, and 4.0 D are strong polar molecules. Carbon monoxide is very low, 0.1 D, propylene 0.4, and toluene is 0.4 D. Okay, this is light polar. Carbon dioxide, neon, nitrogen, and octane are non-polar. Okay, that mu is equal to 0. Okay, so okay, right? So the dipole moment I discussed impermanent dipole moment, intrinsic properties of a molecules, right? So a net separation of charge may be induced in any molecule by application of external electric fields. Okay, so this is called the induced dipole moment. Okay, mu induced, and this is approximately the proportional the strength of the applied field. Okay, right? So for the molecule A, mu A induces alpha AE, where E is the applied field strength and alpha A is the polarization of A. Okay, right? So the source of the field can be calculated using this formula here. Okay, right? Okay. So if A are both polar, then mu A, mu B is not equal to 0. Then the complete expression for the potential of induced is this. Okay, this equation here. Okay, so polarization alpha, like the permanent is mu is the intrinsic property of a molecules. Okay, right? So okay, right? There are two types of dipoles moments, right? So far, permanent and induced. But both can be rationalized and treated by the method of classic electrostatic, and both produce contributions to mu proportional to R minus 6, right? But there's a third kind of pole, an instantaneous pole, okay, which we call it as dispersion, okay, right? So this is the dispersion potential, which you can use this equation here. Okay, right? Okay, this is 3 over this equation, okay, right, for large operations. And then R is the first ionization potential, the energy required to remove one electron from a neutral molecule. So R is basically 1 to 4 10 power of minus 10 joules. Okay, so with this, right, so we have 3 types of the potential with electrostatic, these formulas, induced, and dispersions. Okay, that's for uh, mu for the long range. It can be written into minus C6 over R6. Okay, where 6 is this equation here. And then we can have a ratio, can I? Ratio FL to these values, which is the sum of these all the potential here, and induced and dispersions. Can I? So if we do the uh, uh, ratio fractions here, then we can use this, and this is the approximate equation for that. Okay, that's for this for electrostatic and dispersions. Okay, so the dimensionless FL and dispersion is a measure of effective polarity of a species. Okay, right? So in all cases, the magnitude of the dispersion extraction is substantial. Even when F is small, this extraction can be rarely be ignored. Okay, right? The fraction contribution F induced extraction is generally small, never exceeding about 7%. Contribution of permanent dipoles at near ambient temperature to mu L and mu induced are small, less than 5% of the total for values of less than 1D. Okay, therefore, the substance such as polypropylene and toluene are commonly classified as nonpolar, even though they have significant dipole moments. Okay, so this is the table showing the long range attraction of polar molecules here. Yeah, you can see here this is the ratio in D, I, C6, FL, and induced and dispersions, and this is the ratio here. Okay. Okay, the next section will be on second variable coefficients from potential functions. You know? So the molecular volume of a fluid depends on the behavior of its constituent molecules and is therefore influenced by intermolecular forces. Okay, so this can be denoted by the by this function here B. Okay, right? So when B Okay, right? Is 2 pi and A is the Avogadro numbers. Okay, so this is the remaining terms. Okay, right? So, okay, so this is second variable to the pay potential function. Okay, right? So this is 2 pi and A is the Avogadro number, K is the Boltzmann constant, and this equation here. Okay, so this is a rectilinear potential function, those in which UR is defined by a collection of straight line segments, and one can obtain a closed form analytical expression for VT. Okay, right, so for mu, for the square well potential, okay, right, this for R less or equal to D, then this is the line here, so become infinity. Okay, right, but for D less than R, but less than L times D, okay, which is this line here, so we is equivalent to minus epsilon here, and further than that, it become 0. Okay, right? Okay, right? So if you can see that this line here is very much similar from the previous line. Okay, right? From the previous graph. Okay, right? You can see that when it's sigma here, okay, right? Less, very close to it, small, the distance is less than a sigma, so it start to be repel, okay, right? So further bigger than sigma, then it's attractions, okay, right? Until it's you reach somewhere here, okay, right? One over here, which is R, okay, right? R is more than L times D here, and then it start to there's no attraction or repulsion anymore, right? Because it's too far. Okay, right. So for that, it can be written in a straightforward equation. Okay, right. So we got this equation here, 2 pi d here. Okay, right. From here, we can see that the sign and the magnitude of B are determined by relative contribution of attraction and repulsions. Okay, at low temperature, attraction dominates. Okay, low temperature, what will happen? Low temperature, this is very small. Okay, right. So this number will be quite big. Okay, right. Dominate, producing negative values of B, and the stronger attraction as determined by magnitude of epsilon and I, L, the more negative is B at fixed T. At high temperature, repulsion dominate. Okay, right? So very low temperature, their attraction. At high temperature, it dominate. That's why for something liquid or whatever, when you heat it up, it still holds together. When the temperature increase, then it start to turn to another phase because it start to, it repels each other. Okay, right? So B approaches the value of this limit, okay, right? Which is the V M here. Okay, M is the volume occupied the mole of hard spheres or diameter D. Okay, right? And then for the ball temperature, the contribution of attraction exactly balanced by both those repulsion and B is 0 for the square well potential in this equation here. So this is the temperature where there's no attraction or repulsion. Can I? Okay. So if we can plot it here, then this is the temperature here. Okay, right? So for this what is this? For this equation, let's see here. Temperature based on the argon. Okay, this is argon. Okay, right? That will be around 300 here, right? 300, so about 400 something. Okay, temperature. Okay, that's just calculation. So it must be easier. We can relate that. Okay. Okay, welcome again. Okay, right, so the next session will be the internal energy of ideal gas in terms of microscopic views. Okay, right. So for microscopic views, then we have a fundamental postulate of quantum theory, which is the energy is quantized. That energy on microscopic scale come in a very small discrete unit. Thus, a microscopic system has associated with it an enormous number of quanta energy, with some to determine the energy level. So quantum energy is basically what is the energy inside the molecules. Okay, right? So okay, right. So we have here when a system is isolated, constrained from exchanging either mass or energy with its surrounding, it exists at one of the energy level allowed it to it. Okay, each energy level of a system as associated with the number of quantum states. Okay, right? So that's a quantum state according to the energy level in it. Okay, so if you watch the movie ants, they go to the quantum state. Okay, right? It's a smaller than the molecules, the energy inside it. Okay, right? So that's why it's very difficult for it to go out, right, from the quantum, because there's an energy attraction in it. Okay. Okay, the number G is known as a degeneracy of the level. An altered and isolated system exists at a particular level. It passes over time through all the G's quantum state categorized by the same energy. So a large number of quantum state is accessible to a system of a given volume in equilibrium with surrounding at fixed temperature. Okay, right? For the thermodynamic point of view, fixing T and V establish the state of the system, including its internal energy. Okay, however, the microscopic equilibrium does not imply a static situation on microscopic scale. Okay, the ceaseless motion of the molecule and their collision with the walls of container result in exchange of energy with the surrounding. Okay, right? So when the molecules bombard the container, so the energy be to be the energy be this transfer, okay, right? So especially when this is the same, is at different temperature. For example, if you have a container at higher temperature and the surrounding is lower, so when the molecule bombard the container, right, so a much higher temperature, so some of the energy is losses to the surrounding. So that's why, right, as the time progresses, okay, the temperature of the gas inside the container will reduce because the energy being transferred outside. Okay, right? Okay, the a value for the thermodynamic internal energy is found as the average of the energies of the accessible quantum state, such as weighted by the probability. And the quantity of fundamentals important to come out of this procedure is the partition functions. Okay, so this is our energy to get out. Okay, so there is a Z, something with a middle somewhere here. Okay, this function here, and G is the regenerative level, and K is the Boltzmann constants. Okay, right. For the internal energy can be denoted into this equation here at constant volumes. Okay, so we have a Z here, the partition functions. Okay, right. So this partition function have two parts here. We have translation, and intramolecular. Okay, right. So and this, right, translation means it move around, and then intermolecular. Okay, right, bombard or whatever. Okay, right, the attraction there. Okay, right. So hence the Z. Ln Z equal to ln Z translation plus ln Z intermolecular minus ln N. Okay, summation. I forgot this terms here, okay, right? This symbol here, how to call it, okay, right? But it's actually just time to each other, where and this is arises because of the summation process. So molecules are treated as distinguishable from one another. Okay, the Z translation can be denoted into this equation here, where Na is the Avogadro number, M is the mass, H is the Planck constant, and Z translation in ln, okay, right, can be written in this part here, and then substitute the previous equation, and then Z can be into this formula here, okay, right? And then Z intermolecular is from the evaluate from the equation, the form of equation 16.3, okay, right? This equation here. Okay, this equation here. Okay, differentiation equation system with respect to the temperature constant V and D yield this equation here. And once the equation 14 apply to the ideal gas state, and then we got this, okay, right? So this UIG is equal to this equation here. Okay, right? So representing the FT, the final term by FT, function of temperature, noting that NAK equal to R, reducing this to this function here. And R is a universal gas function, since H, the enthalpy U plus RT, so we can return it into this form here, right? 5/2. So CP is this, the ratio here of enthalpy to the temperature at constant pressure is equal to 5R plus this. Okay, right? For molecules of ideal monatomic gas have no energy of rotation or vibration and Ft, so this become 0. Okay, right? So that's why for someone, for example, argon, okay, right? the CpIgR is 5.2. Okay, right? Okay. Section 7.5, thermodynamic properties and statistical mechanics, right? For statistical mechanics are derived by application of 5.4 to a large number of microscopically identical systems, right, ensemble to all their many allowed quantum states. The entropy can be written as this, S equal to K ln Z plus V over T. So where Z is the partition function in previous what we know, and U is the internal energy as given by equation 16.14. Okay, right? So with this, for ideal gas, we can get this equation here. Okay, but according to Stirling formulas, right, this, right, making this equation into this. Okay, which we can be arranged into this equation here. So this is the function, and then intermoleculars. Okay, right. So okay, so from these values, then we can see that now, right, from equation 5.40 for the entropy for ideal gas, uh, okay, ideal gas, right, for these values here, and then this for the statistical. So it's, if you look at that, it's very close to each other. Okay, right? So both are acceptable. Okay, for the molecular entropy or ideal gas show calculation of absolute entropies for ideal gas states. Okay, and then the data required for the evaluation of the last two terms on the right are the bond distances and bond angles of the molecule. Okay, this is very much in details. Okay, right, are more on the quantum mechanics. Okay, but we go straight here. Okay, right? The fundamental property relation most intimately connected with statistical mechanics in equation 6.9, which express the differential of Humboldt's energy. Okay, Humboldt's energy is A, right? So the energy is here. And then we can work it out. And then we find that in relation to follow the equation, we may written as U minus Ts equal to these values here. Okay. And then from there, we know that A is minus K. K is the Boltzmann constant. Kt ln Z. Okay, right? Since R is K and A, when A is the Avogadro number, so we can return it into this form here. Okay, right? So for equation 6.39, 2.7 through 6.39 for give energy, have their counterpart analogous equation to the Helmholtz energy. So this, we can rewrite this into this form here, like PU, okay? And then we found that the remaining property become this defining equation, S over R for U over RT minus A over RT, and H over RT equal to U over RT plus PV over RT. Okay, right? So these are all from the Helmholtz energy. Okay, section 7.6, hydrogen bonding and charge transfer complexing. Okay, right? So I think that you have done this in your physical or organic chemistry, okay, right? But let's talk about, okay, what is the electronegativity? Okay, right? So electronegativity is a measure of the relative ability of an atom in a molecule to attract electrons to itself. Okay, so this is notion electronegativity was introduced by Pauling, right, in 1932. So Pauling says that the electronegativity Xp here is in between 0.7 and 4 for those elements. No, okay, right? So the highest will be fluorine, right, 4.0, and the least is the hydrogens here. Okay, right? So some are reactor. Okay, so I will go here. So this is the electronegativity for some of the non-metallic element. Fluorine is the highest and hydrogen is the lowest. Okay. Okay, right? So for this, when we have the non-associating donors and non-associating acceptors and associating species. Okay, right? So so what is it? Okay, did you know a non-associating hydrogen donor species? A is non-associating hydrogen receptor, and D is the species that can associate by hydrogen bonding. Okay, right? So I think you have seen this table before. So we have a D here, non-associating to the non-associating, so there's no hydrogen bonding. Okay, right? So with this, with the non-associating acceptor, and non-associating donors, then you can have the bonding there. Okay, right? Okay, so this is for the examples. Okay, right? So this is NH3 and H2O. Okay, right? The same also for H2O and this here. Okay, this is the examples. Okay. Okay, so the next section is on the behavior of excess properties. As you guys can see here, we have known this already that GE, okay, that gives energy excess over RT is HE over RT minus SE over R. Okay, right? So with this, then we can plot it into in this form here. Okay, so this is the section 1, 2, 3, 4, 5, and 6. Okay, so whatever over here, okay, right? Over here is positive for enthalpy, and this is negative for enthalpy. And for Gibbs energy, above here is positive, then that is negative. And then for the enthalpy, whatever down here is positive, and down here is negative. Okay, right? So with this expression here, and using this equation here also, then we can have the sign that if GE is positive, HE is positive, and SE is positive, then it is region 1. Okay, how about region 2? Region 2 is HE is positive, GE positive, but SE is negative. Okay, right? Positive, negative. How about region 3? Region 3, HE negative, SE negative, GE is positive. Right? Region 4, for this GE, HE is negative, and SE is also negative. Region 5, GE negative, HE is negative, and SE is positive. Okay, right? And then for the last 6 here is that SE positive, SE is positive, and GE is negative. Okay, because it's below 0. Can I? So if we plotted, can I? For example, the data here for, okay, so for this is a non-polarizing and non-polarizing mixture. Can I? This is the small circle here. You can see the small circle is mostly here, this area. And then for the dot here is a non-associative and non-polarizing mixture. Okay, so this is the dot here, mostly at this region here, and a triangle is associating and non-polarizing, and this, okay, right? So and relating and non-associating and non-associating, okay, the square here, okay, right? So we can see that there's a region when we plotted it for GE, SE, and HE here. Okay, right? So we found that about 85% of all mixture exhibit GE or positive HE. Region 1, 2, 3, and 4 VI, about 70% positive GE and positive HE. Right? This positive GE and positive HE are the norms. Okay. Okay, about 60% of all mixture fall in region 1 and 4, with only about 15% in region 3 and 4. All right. I'm sorry, 6, right? So this thus the enthalpy is more likely to dominate solution behavior than is at the entropy. Okay, the NP mixtures, the open circles, can I? NP, which is that? This is the NP, right? Um, tends to concentrate in region 1 and 6. Region 1 and 6 here. Okay, okay, right? And then for such mixture, HE and SE are normally positive while G is positive. Okay, right? And GE over T rarely exceeds about 0.2. If GE is negative, entropy dominance, right? So NA over NP mixture, field circles usually fall in region 1. Okay, field circle, okay, right? In region 1. Okay, right here. See that? This region 1, which all are positive. Okay. Thus, GE and HE are positive as it's normally SE. Both GE and H can be large. ASP and MP mixture, the open triangles, invariable occupied region 1 and 2. With region 2 behavior favor with the polar species is very strong associator, such as alcohol and carbolic acid. In the later case, GE can be extremely large owing to the reinforce of effect of positive SE and negative SE. Okay, right? So this is the open one. Okay, right? The open circles. Okay, this is the one mostly in this area here. Okay, right? Okay, right? 1 and 6. Okay? Sorry, 1 and 2. I can't see very well. Okay, okay. Okay, the mixture continue to polar exhibit diversity of behavior. Okay, right? So that is how we can plot it. Okay, right? How we can see the behavior. Okay. Okay, 7.8 molecular basis for mixture behavior. Okay, right. So uh, we have identified the intermolecular attractive interaction of four kinds: dispersion, induction, direct electrostatic, and quasi-chemical. So a summary list of important points are: of the four attraction interactions, the dispersion forces is always present. It dominates when interacting molecules are nonpolar or slightly polar. The induction forces requires that at least one of the interacting species be polar. Okay, it is normally the weakest of the physical intermolecular attractive forces. For neutral molecules, the simplest and normally the strongest direct electrostatic forces is that operating between two permanent dipoles. Okay, right? These forces can dominate physical attractions interactions if the molecules have high effective polarity. So quasi-chemical forces when present can be strongest at the four attractive interactions. Okay, so however, their existence requires special chemical makeup of the interacting molecules. So hydrogen bonding is the most important interaction of this type, although charge transfer complexity can play a major role in some kinds of the systems. Okay, so this is the behavior of the excess enthalpy. You can look at it for the NP mixture. Okay, so you can read it. This is the explanation for what we see from the previous graph figures, right? Okay, for the ASP and then sovereignty NA, okay, you guys can read it, okay, right? And then this also the behavior for the excess entropy, okay, right, how they behave. So they have the list of each, okay, right? So the definition, the explanation is here. So take your time and do your readings, okay? Okay, the last section for these chapters will be on molecular simulations. Okay, right? So for chemical engineer, you seldom do this. This is mostly done by the physicians, the people working in physics. Right? So we are not really concerned on the molecular level. What we're more concerned is more on the statistical. Okay, right? The overall of the things. Right? But with this simulation, there's a lot of methods that can be used, like for example, Monte Carlo. Okay, right? So I think this is not quite important for you if you're working later, because most of the software, like for example, Hyperspanisis, okay, right? So they have all the data in there, so we just can take, okay, right? So we don't do any simulation. But if you want to do your PhD or for your master, then in molecular, then it will be very good, okay, right? To know this for your level. So just to inform you that the simulation and molecular level does exist, but it will be much more complicated. Okay, so this will end our lecture. Okay, right, for this KNC 21113 Thermodynamics 2. Okay, right. So if you don't have any question to ask me, but please read the chapters. Okay, right. So all the best for your final exam, and hope to see you soon.